Welcome to today's session. In this video, we'll dive into LeetCode problem number 397, titled Integer Replacement. This problem challenges us to explore an efficient way to reduce a given integer to 1, using specific operations. We'll discuss various approaches, analyze their complexities, and derive insights along the way. Let's get started. In this problem, you're tasked with transforming a given positive integer, n, into the number 1 using the fewest number of steps possible. You can achieve this by performing one of two operations repeatedly. If n is even, you divide it by 2, and if n is odd, you have the choice to either add 1 to n or subtract 1 from it. The challenge lies in deciding the most efficient operation at each step to minimize the total number of replacements. Let's look at an example to better understand this. For an input of n equals 8, the output is 3. This means it takes 3 operations to reduce 8 to 1 using the given rules. Let's break down the steps to see how this happens. Starting with n equals 8, we first see that it's even, so we divide it by 2 to get 8-4. Next, 4 is also even, so we divide it again, 4-2. Then, 2 is even as well, so one final division gives us 2-1. This process required a total of 3 steps. Now, consider another example with n equals 7. Here, since 7 is odd, we have a choice, either increment to 8 or decrement to 6. Choosing 7, 1 gives 7-6. Next, 6 is even, so we divide it by 2, 6-3. Now, 3 is odd, and we opt to add 1, resulting in 3-4. Finally, 4 is even, so dividing it by 2 gives 4-2. One last division takes us to 2-1, making the total number of steps equal to 4. Continuing with the breakdown of n equals 7, the final division of 2-1 completes the process, bringing the total steps to 4. Let's analyze another example to further solidify the concept. For an input of n equals 15, the output is 5, meaning 5 steps are needed. Starting with 15, since it's odd, we choose to increment, resulting in 15-16. Now, 16 is even, so we divide it by 2, 16-8. Next, 8 is even, so another division gives 8-4. Dividing 4 by 2 gives 4-2, and finally, dividing 2 by 2 results in 2-1. This sequence requires 5 operations to reach the goal. This problem also comes with specific constraints and edge cases worth noting. The input n is guaranteed to be a positive integer between 1 and 2-31-1, which is the maximum value of a 32-bit signed integer. Certain edge cases highlight different aspects of the problem. For example, if n equals 1, no operations are needed, so the output is 0. For a large odd input such as n equals 2 to the power of 31-1, it becomes critical to handle the choice between incrementing and decrementing efficiently to minimize steps. Powers of 2, like 16 or 32, are easier to handle since they can be halved repeatedly with minimal effort. Finally, numbers such as 3 or 15, which involve multiple odd steps, require careful decision-making to select the optimal operation at each stage. Understanding these nuances will help solve the problem more effectively. To solve the integer replacement problem, let's first consider the brute force approach using recursion. The idea here is to explore all possible paths to reduce the number n to 1. When n is even, we divide it by 2. When it's odd, we have two options, increment n by 1 or decrement it by 1, and we recursively evaluate both paths, ultimately returning the minimum steps required. While this approach is straightforward to implement, its inefficiency becomes apparent for larger values of n. The time complexity is exponential, roughly O(2) log n, due to the branching at each odd number, and the space complexity is O log n, to account for the recursion stack. The primary drawback is that this approach redundantly recalculates results for overlapping subproblems, making it highly inefficient. This inefficiency can be addressed by introducing memoization, which leads us to an optimized approach. By storing previously computed results in a dictionary, we ensure that each unique state is calculated only once, significantly improving performance. This method takes advantage of the problem's optimal substructure, which is a hallmark of dynamic programming. The time complexity for the memoized solution is O log n, and the space complexity is also O log n, accounting for both the recursion stack and memoization storage. While memoization greatly improves the recursive approach, it still carries some overhead from recursion itself, albeit minimal. To eliminate this overhead, we can use an iterative approach based on bottom-up dynamic programming. Instead of solving the problem recursively, this method involves a simple loop to reduce n to 1, applying the same rules as before. If n is even, we divide it by 2, if it's odd, we choose between incrementing or decrementing n based on which path minimizes steps. This approach is straightforward in its logic and avoids recursion entirely, thereby reducing space complexity to 1, as no additional storage is required beyond a counter for the steps. The time complexity remains O log n, since the number of operations is proportional to the number of bits in n. However, the iterative approach has its own trade-offs. It can be less intuitive to reason about compared to the recursive method with memoization, and debugging it can be more challenging, especially for those new to dynamic programming. Among the approaches discussed, the memoized recursive solution stands out as the most balanced choice. It combines efficiency with clarity, making it an excellent strategy for solving this problem. By avoiding redundant calculations and leveraging dynamic programming, it achieves optimal performance while remaining intuitive to implement and understand. Although it uses slightly more memory than the iterative approach due to the memoization dictionary, this trade-off is negligible when compared to the performance gains. A key insight in this problem is that odd numbers offer two paths, n plus 1 or n1, and selecting the path that minimizes total steps is crucial. The memoization ensures that each state is computed only once, simplifying the overall logic. In terms of complexity, this approach is efficient, with both time and space complexities of O log n. In conclusion, the memoization approach strikes the right balance between clarity, efficiency, and maintainability. While the iterative approach is more space efficient, it sacrifices some intuitiveness and is harder to debug, particularly for beginners. This makes the memoized solution the most practical and well-rounded choice for this problem. In this problem, we are tasked with reducing a positive integer n to 1 using the minimum number of steps. The operations allowed are straightforward. If n is even, we divide it by 2. If n is odd, we have two choices, either add 1 or subtract 1. Our goal is to determine the most efficient sequence of operations that minimizes the total steps. To approach this, we can use a brute force recursive exploration. The base case is simple: if n is already 1, no further operations are needed, and we return 0. For the recursive case, we handle even and odd numbers differently. If n is even, the only valid operation is dividing it by 2, which reduces it more efficiently. For odd numbers, we need to explore both possible paths, adding or subtracting 1, and compute the minimum steps required for each. This ensures we find the optimal solution by evaluating all possible outcomes recursively. The recursive approach can be expressed mathematically. For even numbers, the number of steps to reduce n is 1 plus the result of a recursive call for n/2. For odd numbers, it's 1 plus the minimum of the results for n1 and n plus 1. With this in mind, we can define a recursive function, min_steps n, to implement this logic. However, recursion alone can become inefficient for larger values of n because the same subproblems are recalculated multiple times. To address this, we use memoization, a technique that stores the results of subproblems in a dictionary. This ensures that each subproblem is solved only once, significantly improving efficiency. It's important to account for edge cases as well. For example, when n is 1, no operations are needed. For very large n, memoization is critical to prevent exponential growth in recursive calls. This approach leverages the problem's optimal substructure, as the solution for n builds on the solutions for its smaller subproblems. To implement memoization, we use a dictionary where the keys represent values of n and the values store the minimum steps required to reduce n to 1. This avoids redundant computations by ensuring that we never calculate the result for the same n more than once. Analyzing the complexity, the time complexity is proportional to the number of unique values of n we explore, which is O(n) in the worst case. Similarly, the space complexity is also O(n), because the memoization dictionary stores results for each unique value of n. Using this optimized recursive algorithm, we can efficiently solve the problem. The recursive function first checks the memoization dictionary to see if the result for n is already stored. If not, it computes the result based on whether n is even or odd, stores the result in the dictionary, and returns it. By combining recursion with memoization, we ensure that the solution is both correct and efficient. To use the recursive function, we define a driver function called minimum_steps_2_1, which initializes the memoization dictionary and calls the recursive function. Let's walk through an example with n equals 7. Starting with 7, which is odd, we have two options: add 1 to get 8 or subtract 1 to get 6. For n equals 8, since it's even, we repeatedly divide it by 2 until we reach 1, requiring 3 steps. For n equals 6, we divide by 2 to get 3, which is odd. From 3, we again have two options: add 1 to get 4 or subtract 1 to get 2. The path through n equals 6 and then n equals 3 ultimately results in fewer total steps. Therefore, the optimal sequence is 7-6-3-4-2-1, which requires 4 steps. By systematically exploring both paths for odd numbers and leveraging memoization to avoid redundant calculations, we efficiently find the minimum steps. This problem highlights the power of combining recursion with memoization for computational efficiency. The recursive exploration ensures we evaluate all possible paths for odd numbers to find the optimal solution, while memoization prevents redundant computations, making the solution scalable for larger values of n. Key takeaways include understanding the distinction between operations for odd and even numbers, recognizing the importance of memoization to handle edge cases and large inputs, and appreciating the problem's optimal substructure. With these principles, we achieve an efficient and elegant solution to minimize the steps required to reduce any positive integer to 1. This implementation solves the integer replacement problem using a recursive approach with memoization. The goal is to find the minimum number of steps to reduce a given number to 1, where the allowed operations are dividing by 2 if the number is even, or incrementing/decrementing by 1 if it is odd. Let's break it down step by step. 1. Memoization. A dictionary memo is used to store results of previously computed numbers to avoid redundant calculations. This ensures the algorithm runs efficiently, reducing the time complexity. 2. Base case. The recursion stops when the number becomes 1, as no further operations are required, 0 steps. 3. Recursive case. Even numbers. If the number is even, the optimal choice is to divide it by 2, 1 step, and recursively solve the problem for number //2. The result is stored in memo. 4. Recursive case. Odd numbers. If the number is odd, two choices are considered: adding 1 to make it even or subtracting 1 to potentially reach the next even number. The algorithm computes both options recursively and selects the one with the minimum steps. This ensures the most efficient path is taken. 5. Memoization lookup. Before any computation, the function checks if the result for the current number is already in memo. If found, it returns the stored result, avoiding unnecessary calculations. By combining recursion with memoization, the solution efficiently handles large inputs, reducing the exponential time complexity of plain recursion to a more manageable linear or logarithmic complexity depending on the input size. This makes it well suited for the constraints of the problem. Here, we begin with the Java implementation of the integer replacement problem. First, we import the necessary classes, such as hashmap and map, which will be used for memoization. Next, we define our solution class and the main function, integer replacement. This function takes an integer n as input and initializes a hashmap to store previously computed results for optimization. We then call a helper function, passing the number n and the memoization map. Inside the helper function, we start with the base case. If the number is 1, we return 0, as no steps are required to reduce it further. After that, we check if the result for the current number has already been computed and stored in the memo map. If it exists, we simply return the stored value to avoid redundant calculations. Moving forward, we define a variable result to store the minimum steps needed. If the number is even, we divide it by 2 and recursively call the helper method, incrementing the step count by 1. When the number is odd, we need to consider both possible operations, adding 1 or subtracting 1. For each case, we recursively call the helper function and calculate the minimum steps required. We then increment the result by 1 to account for the current operation. After determining the optimal steps, we store the result in the memoization map to ensure that future computations for the same number are quicker. Finally, we return the computed result. This approach ensures that we handle the problem efficiently by leveraging memoization to minimize redundant calculations. The overall solution is both recursive and optimized, providing an elegant way to solve the problem within a reasonable time complexity. In this problem, we're tasked with reducing a given integer n to 1 using the minimum number of steps. If n is even, the solution is simple: we divide it by 2. However, if n is odd, we have two choices: increment or decrement it by 1, and we need to explore both options to decide which leads to fewer steps overall. To make this process efficient, we use recursion with memoization. Memoization allows us to store results of previously computed subproblems, so we avoid redundant calculations. Let's start with an example. Take n equals 8. Since 8 is even, we divide it by 2. This gives us helper 8 equals 1 plus helper 4. Next, with n equals 4, we again divide by 2 to get helper 4 equals 1 plus helper 2. Continuing, n equals 2 is also even, so we divide by 2, helper 2 equals 1 plus helper 1. Now, when n equals 1, we reach the base case of our recursion and return 0. Backtracking through these calculations, we find helper 2 equals 1, helper 4 equals 2, and helper 8 equals 3. Thus, the minimum number of steps to reduce 8 to 1 is 3. Now let's analyze the case where n equals 7. Since 7 is odd, we evaluate both helper 8 and helper 6 and choose the smaller result. This can be written as helper 7 equals 1 plus min helper 8 helper 6. From our earlier example, we know helper 8 equals 3. Next, we calculate helper 6. Since 6 is even, we divide it by 2, helper 6 equals 1 plus helper 3. For helper 3 is odd, so we explore both helper 4 and helper 2. Both of these values were already computed earlier: helper 4 equals 2 and helper 2 equals 1. Taking the minimum, we find helper 3 equals 1 plus 1 equals 2. Substituting back, helper 6 equals 1 plus 2 equals 3. Now, returning to helper 7, we compute helper 7 equals 1 plus min 3 equals 4. So, the minimum number of steps to reduce 7 to 1 is 4. Let's examine a slightly more complex example with n equals 15. Since 15 is odd, we compute both helper 16 and helper 14 to determine the smaller result: helper 15 equals 1 plus min helper 16 helper 14. Starting with helper 16 is even, so we divide it by 2 repeatedly: helper 16 equals 1 plus helper 8. From the first example, we know helper 8 equals 3, so helper 16 equals 1 plus 3 equals 4. Next, we solve helper 14. Since 14 is even, divided by 2, helper 14 equals 1 plus helper 7. From the previous example, helper 7 equals 4, so helper 14 equals 1 plus 4 equals 5. Returning to helper 15, we compute helper 15 equals 1 plus min 5 equals 5. Therefore, the minimum number of steps to reduce 15 to 1 is 5. Throughout these examples, we've been updating the memoization table as we go. For instance, when we calculate helper 3, we store memo 3 equals 2, and for helper 7, we store memo 7 equals 4. This ensures we don't repeat computations for these values in the future, saving significant time. The key takeaways here are that even numbers are straightforward to handle since we simply divide them by 2, but odd numbers require exploring both increment and decrement paths to find the most efficient solution. By combining recursion to explore all possibilities with memoization to store intermediate results, we achieve optimal performance while ensuring correctness. This approach balances clarity and efficiency, making it a robust solution for the problem. To analyze the time complexity of this function, we start by understanding the behavior of the recursion and memoization. When the function is called, it checks if the number is even or odd. If it's even, the number is halved, resulting in a single recursive call. However, if the number is odd, the function branches into 2 separate recursive calls, one for incrementing the number and one for decrementing it. This branching means that the recursion explores two paths when dealing with odd numbers, but ultimately memoization ensures that each unique input is calculated only once. The number of unique inputs is proportional to the number of steps required to reduce n to 1, which is logarithmic in nature, specifically O log n. Memoization prevents redundant calculations, transforming what could have been an exponential growth in recursion into a manageable O log n unique states. For each of these unique states, the computational cost is minimal. The function performs constant time operations to determine whether a number is even or odd, to retrieve or store results in the memoization dictionary, and to compute the necessary recursive calls. As a result, the cost per state is O1. When we combine the number of unique states, which is O log n, with the cost for each state, the overall time complexity becomes O log n asterisk O1 equals O log n. Now, turning to space complexity, we factor in both the memory used for memoization and the recursive call stack. The memoization dictionary stores results for each unique input, and since the number of unique inputs is proportional to O log n, the memory required for memoization is also O log n. Meanwhile, the depth of the recursive call stack depends on the maximum number of consecutive recursive calls, which is also proportional to O log n in the worst case. When we combine the space used for memoization and the space used for the recursive call stack, the total space complexity becomes O log n plus O log n equals O log n. Comparing this to a brute force approach, the difference is significant. In a naive recursive solution without memoization, calculations would be repeated for overlapping subproblems, leading to an exponential time complexity of O2 to the power of n, due to the rapid growth of the recursion tree. Additionally, the recursion stack in such a naive solution could grow to O(n) in the worst-case scenario, significantly increasing space usage. By contrast, the optimized approach leverages memoization to avoid redundant calculations, reducing the time complexity to O log n. The space complexity is also minimized, as both the recursion stack and memoization storage are limited to O log n. The best, average, and worst-case scenarios all align with the efficiency achieved by the optimized solution. In the best case, when n is a power of 2, the function only performs having operations, minimizing the number of recursive calls. Here, the time and space complexity remain O log n. In the average case, for a random value of n, the function handles a mix of even and odd numbers. Memoization ensures that the time complexity remains O log n on average, as redundant calculations are avoided. Even in the worst case, where n alternates between even and odd values, memoization still limits unnecessary computations, maintaining the logarithmic complexity for both time and space. Ultimately, the optimized solution is highly efficient, achieving O log n time and space complexity, which is a vast improvement over the exponential inefficiency of the naive approach. One common mistake when solving the integer replacement problem is failing to account for both transitions when the number is odd. Remember, when a number is odd, you have two choices, either increment it by 1 or decrement it by 1. If you neglect to explore both options, you might miss the path that leads to the minimum number of steps. To avoid this, always make sure to consider both possibilities when the number is odd. Another frequent error is relying too heavily on pure recursion without memoization. Since this problem involves overlapping subproblems, repeatedly recalculating the same states can lead to exponential time complexity, which is highly inefficient. To fix this, you can use dynamic programming or memoization to store results of previously computed states and avoid redundant calculations. Lastly, it's easy to overlook edge cases, such as very small inputs like n equals 1, where no operations are needed, or extremely large inputs, like n equals 10⁻⁹, which could cause runtime errors or inefficiencies if the algorithm isn't designed to scale. Always test your solution against the full range of constraints to ensure it performs correctly and efficiently. Another potential pitfall is choosing the wrong greedy heuristic. For instance, always dividing even numbers by 2 is correct, but applying similar heuristics without careful consideration to odd numbers can result in suboptimal solutions. Greedy approaches might seem intuitive but can miss the global minimum number of steps. To address this, it's better to use a breadth-first search or dynamic programming, both of which guarantee correctness by thoroughly exploring all possible transitions. Additionally, some solutions fail to optimize for even numbers, treating them with unnecessary branching when the simplest and most efficient action is to directly divide the even number by 2. This significantly reduces the problem size without wasting resources. To ensure efficiency, always prioritize dividing by 2 when the number is even, as this simplifies the problem without requiring additional computation. When approaching this problem in an interview, there are key patterns and strategies to keep in mind. For even numbers, dividing by 2 is always the optimal choice since it reduces the size of the problem in the most efficient way. For odd numbers, the decision between adding 1 or subtracting 1 should be strategic. For example, adding 1 to an odd number might lead to a power of 2, enabling multiple divisions by 2 in quick succession. This kind of foresight can help identify the shortest path to the target. In terms of optimal approaches, breadth-first search is a great choice for unweighted problems like this because it systematically explores all paths, guaranteeing the minimum number of steps. Dynamic programming is another strong option, as it efficiently handles overlapping subproblems by storing results for previously computed states. It's also important to weigh the trade-offs between these methods. While BFS guarantees correctness, it can be memory-intensive, especially for large values of n. On the other hand, greedy approaches offer speed but require careful handling to avoid missing the global minimum solution. The integer replacement problem shares similarities with other well-known dynamic programming problems. For example, LeetCode 322, coin change, involves minimizing steps to reach a target amount, which also features overlapping subproblems. Similarly, LeetCode 279, perfect squares, focuses on minimizing steps using squares, another situation where dynamic programming is invaluable. LeetCode 91, decodeways, and LeetCode 70, climbing stairs, are classic examples of problems that rely on recursive exploration and memoization to handle overlapping states efficiently. When considering alternative approaches to this problem, breadth-first search stands out for guaranteeing the shortest path in terms of steps, though it can be memory-intensive for very large inputs. Dynamic programming is highly efficient for overlapping subproblems, but it does require careful attention to how states are represented and boundaries are handled. A greedy approach offers simplicity and speed for specific cases but might fail to find the optimal solution in all scenarios. Finally, recursive backtracking combined with memoization balances exhaustive search with efficiency, although it tends to be slower than BFS or DP for large inputs. Each of these methods has its pros and cons, and the choice of approach should depend on the specific constraints and requirements of the problem you're solving. That brings us to the end of today's discussion on the integer replacement problem. We explored various approaches, analyzed their trade-offs, and highlighted key insights. Remember the importance of optimization techniques like memoization in recursive problems. Thanks for tuning in. Don't forget to like, share, and subscribe for more content. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!